Hi guys, welcome back to my channel. Today we're going to be looking at chemical reactions and dilutions, but what we're really actually going to be looking at is using differential equations to examine input versus output functions. So a really simple example here to start. A water tank is being filled with rain at a certain rate. However, there is a hole in the bottom of the water tank through which water escapes at a particular rate. Write an equation to express the volume of water at any time in the tank. Well, if we were looking at the change in volume at any time in this tank here, then the change in volume is really going to be affected by how much is going in, or the rate at which this is going in. So let's draw this. I'm going to draw this as dV dt, and we'll call that the input rate, and then how much flow is going out of this at any given time. So let's call this the output rate. So the rate of change in the container is going to be equal to the input rate, take away the output rate. So really, I think the trickiest thing for these kinds of problems is determining what those input and output rates are. Because once you've found those input and output rates, then you can integrate the equation to find your solution for the total volume in the tank at any time t. This problem now is a little bit more complex. So this is actually talking about the rates of two different things here. So let's go through and let's try to solve this. And again, we can think of this as an input versus an output problem. So there's going to be some sort of subtraction that we're going to have to perform. So a tank has a capacity of 300 litres and contains 200 litres of water. Okay, so let's start writing this information down. So we have 200 litres of water in our tank, in which 100 kilograms of salt has been dissolved. So what I'm going to do is I'm going to pop the salt in black, and then I'm going to leave the flow of the liquid in blue. A salt solution of concentration 2 kilograms per litre is poured into the tank. So this is part of our input. So we have 2 kilograms per litre being poured into the tank at a rate of 3 litres per minute. So that's at a rate of 3 litres per minute. The well-stirred solution flows out at a rate of 2 litres per minute. So the output now is going to be 2 litres per minute. And it's not going to tell us what the output rate of the salt is, of course, because this salt comes in to this container, which already contains salt, becomes mixed with this container, and then flows out. All right, so determine the volume of the liquid in the tank at any time t. So we're going to use our rates to do this. So the first thing that we're going to write is that the change in the volume of the tank is going to be equal to the input rate, take away the output rate. Okay, so in this particular case, if we have a look here, this is our input, and this is going to be the change in volume given a particular time for our input, and that's going to be equal to 3, because that's 3 litres per minute. Similarly, with our output, our change in our output volume in a given amount of time per minute is equal to 2. So therefore, our change in volume per time is going to be given by our input rate, take away our output rate, which is just going to be 1. Now we need to integrate both sides to find the volume at any time c, and we end up with t plus our constant for our value. So let's go ahead and let's work out c now, and we can do that using some information that we've already been given, because we know that when the volume is equal to 0, it already contains 200 litres of water. And so since that's equal to 200, when t is equal to 0, c must be equal to 200 as well. So our volume at any time is going to be equal to t plus 200. State the differential equation now for Q, the amount of salt in kilograms in the tank after t minutes. So I'm just going to clear this and I'll come back. So here our input rate of salt is going to be 2 kilograms per litre, and we've already got 100 kilograms of salt in our container. So if we wanted to find the change in salt in the container for a given amount of time, then that's going to be equal again to the input rate, take away the output rate. So now we're going to have to go ahead and determine what each of these rates are. And again, this is the point where sometimes it can get a little bit more tricky. So if we have a look at our input rate, we've got 2 kilograms per litre going in, right? So that would be our change in mass in a particular volume. But we also have our rate of 3 litres per minute going into the tank. So we've got 2 kilograms per litres multiplied by 3 litres per minute. So that's going to cancel out these litres term, and we're going to end up with 6 kilograms per minute going into the tank. So that's going to be our input rate. So now what we're going to do is we're going to determine our output rate. So we know that this solution is living at a rate of 2 litres per minute. So now what we need to do is we need to determine the amount of kilograms per litre that are leaving in this particular solution. So we can do what we did before and remove those litres term and just end up with the change in mass per given unit of time. Okay, so the number of kilograms at any time in the tank is equal to Q, as we've defined by our question here. And the volume of the liquid in the tank is found by VT. So that was that same function that we've actually just found. So if we substitute in that previous function that we found, so T plus 200, we're going to get the output is equal to 2Q over T plus 200. All right, so now we've got our input rate, which is going to be 6 kilograms per minute, and we've got our output rate, which is going to be 2Q over T plus 200. So we've gone ahead and we've now found our differential equation for Q, the amount of salt in kilograms in the tank after T minutes. Let's do one more example. All right, so here we have one more input-output problem. So a vat contains 15 litres of pure water. A sugar solution containing 5 grams per litre is poured into the vat at a rate of 4 litres per minute, and simultaneously the well-stirred mixture is leaving the vat at the same rate. And so the first thing we're going to do is to set up the differential equation for the amount of sugar Q in grams in the vat at any time T minutes. So in other words, we're setting up dQ dt, and so we need to find the input rate and we need to find the output rate. And so something really important to note, since these units are effectively in grams per minute, when we do our input and our output rates, we also want to make sure that those are in grams per minute as well. So that's why I've been using that chain rule to eliminate those litres variables in the earlier equation so that I could have it in a given mass per unit of time. So let's go ahead now and let's solve this particular problem. So starting off with our input rate, we know that we've got 5 grams per litre of the sugar entering the tank, and we've got this inflow rate of 4 litres per minute. So when we multiply those, we're going to end up with 20 grams per minute is going into the tank. So our input value is just going to be 20. Now the output rate is going to be pretty similar to what we have seen in the previous equation. So we've got this leaving at 4 litres per minute. And so what we need to do is we need to set up the amount of concentration of the salt in the tank. So in this case, I'm going to let Q equal the mass of salt in the tank in grams at any given time T. So we're going to multiply that by the mass in grams. Then we have to divide that by the volume in litres. So that's going to be given by the equation of this volume. So what we need to do now is we need to go ahead and we need to determine what the value for VT is going to be. Now, in this specific, In this specific instance, we have this inflow rate is going in at 4 litres per minute and it's coming out at 4 litres per minute. And so the volume at any time in the tank is actually just going to be 15 litres. So we've got 4 litres per minute, so 4Q over 15, and that's going to be the amount of grams per unit time. So this is going to be our output rate now. So we've got 20 take away 4Q over 15. All right, so I've just gone ahead and I've just rewritten this a little bit neat and tidier. So let's go ahead now and let's answer this next problem. So solve the differential equation to determine Q at any time T. Now in the last problem, our differential equation had 2 variables that had to be separated out, so that it was a little bit more complex. But here you can see we're only going to be required to integrate this problem with respect to Q. So let's go ahead and rewrite this using the integrals. All right, so here we have our differential equation. Now in this case, we've only got our variable q, so we're going to need to integrate with respect to q and then rearrange. So to do that, the first thing that I did is I popped both of these into fractional form because I'm going to flip this differential. So I have dq is equal to 15 over 300 minus 4q. So now what I can do is I can go ahead and I can integrate with respect to q, and that's going to remove that term, and then I'll end up with my integral. Last thing we need to do now is determine C. So to do that, let's just go back and read our original question to determine the concentration of salt. So a vat contains 15 litres of pure water. So there you go. So it doesn't contain any salt whatsoever. So when T is equal to 0, then Q is also equal to 0. So I can substitute in now and go ahead and solve for C. So C is going to be equal to about 16.19. Now this is kind of ugly to me. I don't like having to remember to use all those decimals. So just to avoid rounding errors, what I'm actually going to do is substitute this into the function instead. So we've got T is going to be equal to negative 15 over 4 ln 75 take Q, whoops, plus 15 over 4 ln of 75, and that's going to be a nice exact answer. So that's our expression in terms of T. So we need to go ahead now and we need to rearrange this to solve for Q. So just to quickly summarize what I've done before I go too much further, I've gone ahead, I've multiplied both sides by 4 over 15, and then I've rearranged and used my log laws to express this in this form. Last thing I've done is I've raised e to the power of each side, so this is what I end up with. So the last thing I need to do now is just to continue to go ahead and rearrange to solve for Q. So to do that, I've just multiplied both sides by 75, take Q, taking this over to the other side. Then rearrange to solve for Q. So to do that, I have moved this 75 over to the other side and divided through by -1. Now when I flip this to the bottom here, this is the same as effectively having a negative power, and so that's why I've moved this to the top line and I've written negative 4 over 15t. So that's where I've got these values from. And the last thing that I could do if I so wanted is I could factorize out the 75, so we have 1 minus e to the power of negative 4 over 15t. So that's just some algebra and some rearranging. Really what I want to focus on for this video is that whole process of finding the input rate versus the output rate. So if you want a little bit more detailed information about rearranging, then I can do a separate video for that. So now that we have this value for Q, we can go ahead and we can answer our last question. So me just scrolling up here. Our last question was, after how long is the sugar concentration 4 grams per litre? Something to be really careful of with this problem, and I know it's really tempting to do this because this is the first thing I was tempted to do, is just to substitute this 4 grams per litre right away into that Q. But remember what we defined Q as. Q was just defined as the mass in grams. It wasn't actually defined as the concentration. So if we go back to our tank, we have 15 litres of pure water at any time in the tank because the input rate is the same as the output rate. So if we've got 4 grams per litre and we've got 15 litres in the tank, then in total we're going to have 60 grams in the container. So then QT is going to be equal to 60 grams. So let's write this in now. So we have 60 is equal to 75, 1 minus e to the power of negative 4 over 15t. So now all we need to do is just to go ahead and rearrange and then solve for t. Okay, so now that I've substituted 60 into the equation, I've gone ahead and rearranged, and I've gotten t is equal to 6. And I just want to double check those units that we're using. So we're using minutes, so we're going to reach this point of 4 grams per litre after about 6 minutes. So there you go. So that's some input versus output problems that we've solved using differential equations. And really the trickiest part of this is finding what those inputs and those output rates are, and then going ahead and integrating that to solve for our particular function. All right, guys, I will see you in the next one. Have a good day.